This next one is another system where we're pushing two blocks and we want to know what happens to them and how much contact there is between the two of them. So here's the problem drawn out. We've got a 2 kilogram block that's up against a 5 kilogram block, and we're applying a 21 Newton force directly to the 2 kilogram block. And we're going to assume no friction here just to keep things simple. The two questions are, what's the acceleration of this entire system? And what's the force of contact between block A and block B as they press against each other? Since the two blocks are going to be touching the entire time, then the solution is really the exact same as if we just had one object that looked like this with a mass of 7 kilograms. There's really nothing to distinguish the two, which means we can just use Newton's second law to get that acceleration. If I do that, then the total mass of the system is 7 and the net force on it is 21 because there's nothing pushing it left or right besides that. So I get an acceleration of 3 meters per second per second. So far, so good. Now that we know the behavior of both of the blocks together, we have to figure out what's happening with the individual blocks and draw their individual force diagrams. For the white block, I can easily get three forces. We have a downward force of gravity of 20, of course, and since the block isn't accelerating up or down, it's not flying off the table or anything, then we can assume there's a normal force of 20 in the upward direction, so these two are balanced. There's also a push to the right acting on this white block of 21 newtons, and there's an extra force that I haven't drawn yet. And that is the force of block B on block A, because there's a point of contact here between those two blocks. There's force going on between them. The blue one doesn't want to be moved, so it's pushing back on it, and we've got to figure out how strong that is. And Newton's second law is once again going to come to the rescue on this one. Once I do a little bit of math, I get a net force of 6 newtons on the white block. And the direction of that net force needs to be to the right because that block is accelerating to the right. So the forces are stronger that way, which means the force of B on A is going to be 15 newtons. In case you're still feeling a little queasy or maybe you're not quite convinced, let me draw a force diagram of the yellow block to see if that 15 newtons matches up. On the yellow block, I get these three forces. There's a downward force of gravity and an upward normal force, no surprises. And there's the white block pushing on the yellow block. And remember how Newton said that these two are the same? The force of A on B is the same as the force of B on A. So this thing's going to be 15 newtons. If I use Newton's second law, then I get 15 is equal to 5 times 3. And that sounds like a happy ending for me. So the force of contact between these two blocks is 15 newtons. But I have one more question that I'm going to throw out there. What if I were to change the problem up and make it so that we're pushing on the system from this way? Would the answer be different if the blocks were still the same, but we pushed on it from the right? Let's find out for fun. So what if we had a situation that looked a little bit more like this? Would the contact be different? Well, let's work it out in the same way that we did before. You have a 21 Newton force, and that's the net force on the system. And it's on 7 kilograms worth of blocks. So we just use F net equals MA. So we get 21 equals 7A. And lo and behold, we get the exact same acceleration that we did before. That shouldn't really be a big. So again, I draw the force diagram for the yellow block. We got downward force of gravity, upward normal force, business as usual. And this time the yellow block's being pushed with 21 newtons to the left, and the white block is pushing on the yellow block with some force that we are trying to figure out once again. But we can take advantage of the fact that we know that the acceleration is 3 and just run Newton's second law. After doing that, I get a net force on the yellow block of 15 newtons to the left, which means the force of A on B over here had better be 6 newtons to the right. Well, wait a minute. That's quite a bit weaker than the contact force we got before. When we were pushing from this side, we had a contact of 15 between them. And now, if I push from the right, there's only a contact of 6. So what the heck is going on here? Well, I want you to think about it this way. When a hand pushes on this stuff, you're acting on both of the blocks. But the only reason that you can push on the second block that you're not directly touching is because that force is transmitted through this block. Now, if you look at the example on the left, you have 21 total newtons of force, and it's sort of like some of them are going to accelerate the 2 kilogram, and some of them will be used to accelerate the 5 kilogram. It's like they're getting distributed. Now, the contact force between them is the agent that does that distribution. So in this case, most of those 21 newtons have to be transmitted on through to the yellow block. That's why you get a very strong contact in this first case. But in the second case, most of the 21 newtons are simply going into speeding up the 5 kilogram block. It's like the 2 kilogram is just a small nuisance that's in the way, so there doesn't have to be much contact between it. If you ever want to prove this to yourself, stick your hand between two blocks of different mass and try pushing on them. You will notice the difference quickly.